All right, in this video, we will define how to evaluate improper integrals. We'll define improper integrals of type 2, and we'll be doing examples. So let's review what we have done. So we've looked at a region like this, where we have an asymptote on one side. So when we look at the integral, the function's not continuous at 0. What we did is we replaced 0 by t, computed that, and then said I'm going to let t approach from the right, and that is going to give me my value. All right, so we've written it in the takeaway here. We have that the integral from a to b of f of x dx, where a is the discontinuity, should be evaluated as the integral from t to b, and then we take t, go to a plus. So note that we take the limit as t approaches a from the right to ensure that the interval from t to b, which is a new interval of integration here, avoids a discontinuity x equals a of f of x. So if b is the discontinuity of f of x, then we would have to take t smaller than b. So t would approach b from the left, right? So if b is the discontinuity and this is a, you want to stop before so that your interval here has no discontinuity. All right, we're ready. Definition 7.2.1, improper integrals of type 2. Assume that f is continuous on AB, but not necessarily at a. Then the integral from a to b of f of x dx, that will be the limit. I replace the problem bound by t, and then I just take a second to remember if the bound is the smallest one, then t must be bigger than that bound to be closer to b, so I'm going to take a plus. Same thing if b is the problem point, so assume that f is continuous on ab but not necessarily at b, then the integral from a to b of f of x dx is the limit. I'm going to take a's, leave it alone, then t instead of b since b is the issue, and then I'm going to take t goes to b, and I want left here, I want the t to be smaller. All right, the integral a to b is convergent if the appropriate limit gives a finite number. It is called divergent if this limit is plus infinity, minus infinity, or if it doesn't exist. Third case that we haven't considered yet is what if the discontinuity is bang in the middle of the interval? All right, so assume that f is discontinuous at c in AB. And now we're going to look, just like we did when the two bounds were infinite in type 1, I'm going to look, so that's not an E, that's a C, at the integral from a to c. That's going to be one of these types, and c to b separately, that's going to be one of these. If both of these give you a finite number, if both of these converge, then the integral will be the sum of those finite numbers. Right? And the integral converges. Otherwise, we say that the integral diverges. All right, so this third case is a lot like the case where you have two bounds being infinity. All right, so the second type of improper integrals requires more care as their bounds are finite numbers, right? We saw it in each of the examples. This looks like a regular definite integral. So does this. At first glance, you could plow ahead, do this, get 0, get the wrong answer. And so it's a bit more of a trap than type 1 where you have a big infinity as one of your bounds. So you need to determine yourself where the discontinuity lies. All right, so remember to look for the following issues. If you have a fraction, find when the denominator is 0 in your interval. All right, so every time you have a domain issue, like you're dividing by 0, then you might have an asymptote. You might have a discontinuity. Case number 2, for logarithms, find when the interior of the log is 0 in your interval. Again, log of 0 doesn't make any sense. If your interior is 0, then you have an issue there. For trigonometric functions, those often have discontinuity, so write them as a fraction of sine and cosine and use the first case. So if you have secant, cotan, tan, and cosecant, these all have discontinuity because you can have them as a fraction of sine and cosine, and then as soon as you have a fraction, you'll have zeros for the denominator. All right, let's try an example. I want to evaluate the following improper integrals. Sorry. All right, so I have the integral from -8 to 0 of 1 over cube root of x. All right, so we have a fraction. So I want to check, is cube root of x the denominator? Can it be 0? That means x is 0 cubed, which is 0. So we have our discontinuity. There's only one. It is in our interval, and so we have to worry about it, but it's only at 0. All right, so this is my problem bound. I'm going to replace it by t. Let me write the exponent as -1/3, and then I'm going to have t go to 0. Now you have to decide if it's 0 plus or 0 minus. Whenever it's the bigger bound, it's a minus. Whenever it's the smallest bound, it's a plus. You want to make it closer to the other bound. All right, now we have a regular integral with the limit in front. So I'm going to take x to the 2/3 over 2/3 from -8 -8 to t. And so I'm going to get the limit as t goes to 0 minus of t to the 2/3 over, well, let's put it as 3/2 minus. All right, if I put -8 here, that's going to be cube root of -8 squared over, well, put 3/2 like this as well. If I put in 0, this part is quite nice. It's just a positive power, and so that's going to give me 0. And then I have -3 cube root of -8, that's -2 squared over 2, and I get -6. All right, so you have an integral with bounds, and you have a limit. That's it. All right, let's look at another case. What if I have the integral from 0 to e? Let's look for discontinuities. I have a logarithm, and so I need to make sure x isn't 0, so I do have one. Again, it's x equals 0. But this time 0 is in the denominator, and so I'll have, in the bottom bound, sorry, it is lower. So I'm going to replace that by t. Since it's the smaller bound, I'm going to say 0 plus, closer to e than 0. And now I have to evaluate this integral. All right, this is IBP. I have a product of log with a trig, so I'm going to take u. This is IBP, integration by parts. U is going to be ln of x. du is 1 over x dx. dv is x dx. And v is x squared on 2. And so I'm going to get a limit as t goes to 0 plus. I'm going to take this product minus this integral. So ln of x, x squared on 2 from t to e minus the integral from t to e of x squared over 2, 1 over x dx. And so I get the limit as t goes to 0 plus x squared log of x divided by 2 minus this here. Actually, let me do it. It's just x on 2. And so we get the limit as t goes to 0 plus, sorry, lost my bounds again, x squared ln of x divided by 2 from t to e minus x squared divided by 4 t to e. Perfect. All right, now plug in the bounds and take a limit. Let me use a bit more space just because it's hard to tell how much room I have left on this thing. So I get e squared ln of e divided by 2 minus t squared ln of t divided by 2. All right, that's the first one. Second one is e squared over 4 minus t squared over 4. All right, I want to send t to 0. This doesn't have any t. I'm just say that's 1, by the way, so it's e squared over 2. This has 2 t's. I get 0 times infinity, so I'm going to need L'Hopital here. This doesn't have any t's, and this is just going to be 0. So I'm going to worry about that middle one. Like I thought, I'm a bit running low on space, so let me bring this up a bit. All right, so let me do that harder one on the side. All right, so that's infinity times 0, and so I'm going to bring one of the two to the denominator. Never bring log unless you really have to, so t to the minus 2. Now I have infinity over infinity. I get 1 over t minus 4 t to the minus 3, and then that's going to give you, sorry, 0 plus 0 plus 0 plus. That's going to give you t cubed over t, so t squared. Let's leave the minus 4 here, so that's 0. All right, so this part is 0, this part is 0, and so what I get is e squared on 2 minus e squared on 4. And so that's e squared on 4. All right, so again, all these problems with logs, they're not obvious, they're not easy. They often require L'Hopital's rule. All right, so I have one last problem. Let's cut this video here, and then we'll look at our original problem with a secant squared to see why it gave us 0 and what's the real answer.